Yeah, so hello student, welcome to the today's class. So today we'll learn a new idea, perhaps one of the most important idea in group theory. So it's called group actions. Okay. So what do you mean by group actions? So you have a group G and a set X, and we say that G acts on X from left side or from right side, whatever. If there exists a map from G cross X to X. Okay. And from left side for right actions you map from x plus g to x. Okay, and usually that denote by the notion this notation g x is g dot x. Okay, this is a notation of group actions. Okay, this is not the usual group operation on g, because x may not be element of g, right? So you don't have this, but this is the actions. Okay, so and this the operator need to satisfy these following two conditions. Then we say this is a group actions. What are the conditions? So condition number one, that the for identity acts on any element of x trivially. So what does that mean? That means 1 dot x equal to x for all x belongs to x. Okay, and I is the one is the identity of g. And the number two property is very important property. So it's kind of associative property. What does that mean? So suppose you have two elements, any two elements g1 g2, and you want to first take the action on g2 on x and then g1 on x, and this is same as taking the group operation g1 g2 and then taking the action on x. Okay, and this is for every g1 g2 belongs to g and every x belongs to x. So if this map satisfy these two property, then we say that this is g is acting on x from left side. Okay, and from right side also you can do the other way exactly. This is for this right actions. For right action, what you do exactly this x dot 1 equal to x. Okay, and number 2 is x dot this whatever, so g1 g2 is same as x dot g1 and x dot g2, sorry, in dot g2 dot g2. Okay, so similarly you can define the right action also, but unless until we are mentioning our actions will be always the left action. Okay, and thus whenever we have a group acting on a set, then we say that x is a g set. We say that x is a g set. Okay, and we write down by this notation: g is acting on x from left side or g is acting on x from right side. Okay, so let me now tell some of the examples. So perhaps this one of the most important example is called the conjugation actions. So what is that conjugation actions? So g, here I am taking the x is also g as a set also. So g is acting on x, which is g itself. So g is acting on g by conjugation. What does that mean? So that means that the action g dot x is nothing but g x g inverse for all g belongs to g, and x also belongs to g. X is also element of g, right? Conjugation action, and this is going to help us many places in near future soon. Okay, and now there will be many other actions. So let me tell one more actions, few more actions. So G is a group, and you have a subgroup H on G, and then you take the collection of distinct left cosets. X is my that set, which has all the distinct left cosets of H in G. Then I am writing that G is acting on X via this operation. This is what? So you have a left cosets H and you have an element of group G. Then the action will be the natural action. So GA is an element of G, and then cosets of this, right? So this is very natural actions. Okay, and one more action. So the third example is called left regular actions. What is that? So here also G is acting by G by just group operation. G dot x is nothing but gx. Okay, now let me define one more action. So Suppose my group is G is Z mod PZ, that group of residual classes modulo P with this uh, addition modulo P, and where P is say rational primes, rational prime, okay. And so I will choose my actions G. I will choose my set X. So let me write down the set X. So X is collection of P tuples. Okay. So let me write down by this X1, X2, XP. So this is collection of P tuples where this Xi is an element of some set. So let me write down, maybe say Xi is an element of up to n. I am writing up to n because this is going to help me. I am going to use this soon. That's why I choose this set. You can choose many other set also. And so whenever you have p tuples, then Z mod pz acting on, always acting on that via something called shift operator, left shift operator, okay, or right shift operator. Both you can say. Okay, so what is the action? So action C. Now you recall that this group G is actually cyclic group, right? Generated by one bar. So it is enough to define the action of the generator, because everything will follows from the generator. And what will be the generator? Action of the generator. So one bar acting on any element x1, x2 dot xp via a shift operator, left shift. This is I am defining. Okay. So the first element will come. The first x1 going to second place, second going to third place, and so on. And this is p minus 1, and last one comes to first place. This is the action. So this is, you understood that you just shift the coordinate in one places, okay. And obviously instead of one bar, if you choose two bar, then it will shift. So what will be the two bar action? So it will shift each coordinate by two places. So one, the first x1 going to third place, the second x2 goes to fourth place, like that, okay. So this is called shift operator actions, okay. And you can do by right shift also. This is, I choose left shift, you can do right shift. For example, 2 comes to first place, 3 comes to first, second place, and so on, and x1 goes to the last place. That is also possible. That is called the right shift operator, okay, right shift operator actions. So anyway, this, whenever you have p tuples, you can always define actions of Z mod pz on that p tuples by this shift operator, okay. These are all, there are lots of applications, so I will come back to this. Now let us do some nice algebra. So now say now let G is acting on a set X, okay. So what does that mean? That means you have a map from G cross X to X, okay. Then we define a relation, say tilde on X by what? By this. So by, we say that this X is related to Y if Y equal to, say, G dot X for some G belongs to G. So what does that mean? So that means that I am saying that two elements of the set X, two elements of the set X is having this, they are related to each other if one can be written as a image of the another under the actions, under the group actions, okay. Whatever the actions, so this G dot can be any actions, okay. So in this case, this is one of the relation I am defining on X. Now let us check what kind of relation is this. So maybe let me just do it. So whether this is a reflexive action or not, let me check, reflexive or not. See, so what does that mean? That means, yeah, so you see that for any X, so X related to X as you can write down x equal to identity time x, right? For all x is x. So what does that mean? That means given any element of x is always related to that. Okay. So this means this is a reflexive actions. Okay. And we check whether it is symmetric or not. Symmetric. Now if x is related to y, this implies y equal to some g dot x, okay, for some g belongs to g, but that implies that x equal to, it is multiply both sides by g inverse, and then if multiply by both sides by the g inverse dot x y equal to g inverse g dot x, which is nothing but 1 dot x, but for the first property it is nothing but x, right? So what does that mean? That means x is related to y implies that uh, yeah, so that means that, see, x is equal to g inverse of y. What does that mean? That means y is related to x. So what does that mean? That means this relation is also symmetric. Clear? So whenever x related to y, then y also related to x, right? Now let me check another property, say transitive property. Transitive property. What is transitive property? So it is given that, uh, say x1 related to x2 and x2 related to x3. And now we need to check whether x1 is related to x3 or not. So what is the meaning of that? So what is the meaning of this x1 related to x2? So that means that your x2 will be equal to some g1 dot x1, right? And what is the meaning of this x2 related to x3? That means x3 will be of the form some g2 dot x2, right? So thus you can write down x3 is nothing but g2 dot x2, where x2 equal to g1 dot x1, right? And hence you can use the second property of the group actions that tells you that it is nothing but g1 g2 dot x1, right? And thus x1 is related to x3. Clear? So that tells you that this relation is also transitive. So what is the final result? So thus this tilde is an equivalent relation on x, right? This is okay, everyone? Yeah. So I hope you understood so far that whenever I have a group actions, whatever action may be, doesn't matter, if always define the equivalent relation on x. Okay. Now we already learned this thing that whenever I have equivalent relation, then I have something called partition, right? So this equivalent relation, this equivalent relation forms a partitions equivalent relation are not this forms a partition on x, okay, and so those are equivalent classes, right? And um, so partition on x, we had equivalent classes. So let me write down full thing. uh, equivalent classes, those classes are partition, right? So these classes are called orbits. Okay. So what is the orbit of this group action? So orbit of this group action is nothing but the equivalent class under the equivalent relation what we just defined, right? Okay, and how do you write down? So we write down this by this notation. So gx, and this is what? This is the equivalent class of x. So what does that mean? That means it is element of this form gx such that g belongs to, so gx, I mean g dot x, g belongs to g. Okay, so you have a x element, and then you collect all the actions of all the action by any element of g on x, and this collection is called the orbit of x. Clear? So obviously you can easily find out that in this orbit obviously x belongs to this, right? X belongs to gx. This is clear. So this gx is always non-trivial. Sorry, always non-empty. It's not empty always, right? So you add this happen element. Okay, so what does that mean? That means so you have a group G. So let me just um, draw a picture here. So group G, and G is acting on this set X, and then you have this kind of partitions. These partitions are called the orbit. Okay, these are the orbit, and then you have X kind of union of these orbits, Gx1, Gx2, and so on. Something Gxk, right? Okay, clear. Okay, okay, I will come again. But now let me ask you a few interesting questions. So, okay, so if so now start with that both G and X are finite, then what happened? Then do you have some nice thing or not? Okay, so if X and G are finite, then you can have natural questions. What are the natural questions? So you can ask, say, like how many elements are there, or how many equivalent class are there, right? So maybe say how many equivalent equivalence classes are there, right? Simple question you can ask, or you can ask, say, um, how many elements are there in each orbit, how many elements are there in each orbit. So this is a natural question to ask. So because I mean I don't know. So this is going to help me. So I don't know how many such things is there right now. So we need to find out whether we have a formula for counting the number of elements in orbit or number of equivalent classes. Okay, and this leads to us to define this idea called stabilizer. Okay, so let me define it. What is stabilizer? So stabilizer. Okay, so again, so how to define? So you have a group G acting on a set X, and you have an element of X. Okay, so we define the stabilizer of X. The stabilizer of x is so we denote by this notion, denoted by g suffix x. Okay, and how to define it? So you define is kind of set of all elements of G which fixes X. So what does that mean? And define as like this. So Gx by definition, you collect all the G belongs to G such that which fixes X. What does that mean? That means G dot X is X. Okay, clear? So you have all those G's, you collect all the G's and you check that how many elements are there which fixes X, and obviously this is non-empty, as identity always belongs to stabilizer of any element, right? Identity belongs to there, identity always fixes. Okay, so what does that mean? That means I am asking that how many such okay, so okay, I will answer those questions. So or maybe I can define some more. Okay, let me just answer some of the questions and then we will check whether the number of elements or whether the number of elements in the orbit are known to us or not. So let me just check it, give you some idea. So obviously I hope this is you understood that you collect all the you choose an element, you define the stabilizer of that element by the element of G which fixes that same element. Okay, and the stabilizer is always non-empty because identity is always belongs to stabilizer of any element, right? Now let's come back to one of the questions, that how many such elements are there in any orbits. Okay, and then we can ask okay, so maybe okay, so yeah, so before coming to the answer, maybe I just want to tell you a few things. So uh, what about this this stabilizer of any element? So we need to check it. So let us check that this is always subgroup of the group G's. Okay, and the answer is yes. So this is subgroup. This is always subgroup of G. So how to check it? So let obviously you already saw this is non-empty, right? Identity is there. Now let you check that some G1 and G2 belongs to stabilizer of X, and then what you do, so you show that G1 G2 inverse belongs to that, right? So what does that mean? So that is G1 dot X equal to X, and also G2 dot X equal to X, right? Because they are element of stabilizer of X. But this the second identity you can write down as multiply by G2 inverse both side, and then you will have G2 inverse dot X equal to X, right? This is I am just using that property number 1 of the group actions. Okay, so with that help of this property, can we check whether G1 G2 belongs to Gx or not? So thus you check that G1 G2 inverse of X is nothing but G1 dot G2 inverse dot X, right? But G2 inverse dot X equal to X, so this is nothing but G1 dot X, which is nothing but X, right? And hence G1 G2 inverse is element of Gx, and thus the stabilizer is a subgroup of G itself, right? That is okay. Yeah, So what does that mean? That means you can actually count how many such elements are there, and also you can count the total number of elements of X in terms of the stabilizers. Okay. So yeah, so maybe I can so this is subgroup we have done. So um, yeah, so now yes, so maybe I can send write down by this. So now you see you have a natural map. So now uh, there is a natural map. What is the map? So from g of x um, to this uh, let's say, okay, so g of x to um, maybe I will come here later. No, let us just fix it first. So what type of map you can define from g of x to uh, g. Okay, so this is I'm not writing as quotient group. This I'm writing as collection of left cossets. Okay, so let me write down by this notation. Okay, collection of left cossets of this. So this is my kind of collection of left cossets of gx in G. Okay, so x is given, obviously given any x belongs to x, so I have a natural map. So this is the cossets. Okay, and so what will be the natural map? So let me write down. So recall how these elements of this look like. So the element of this look like something g dot x. Okay, and how this element of this look like? This look like, so this map to g into gx, right? Cossets of gx with respect to small g. Clear? So this is very natural map, right? So you choose an element of the orbit, you send is a cossets of gx. Now you see what type of map is this? This is a homomorphism. Not, so let me write in this phi. Say maybe say phi. Okay. So this is my map phi of g dot x is g of gx. Okay. Now is this a homomorphism of okay, so yeah, so I don't know whether homomorphism or not, because this is, I don't know they have a group structure or not. This is may not be a group, right? Because gx may not be an all subgroup, right? So, but what other thing you can ask? You can ask whether phi is injective or phi is surjective, something or not. So let us see whether phi is a injective map or not. Now, so let so to prove something is injective or not, what did you prove? So you start with say phi of g1 dot x equal to something phi of g2 dot x, right? For some arbitrary g1, for some g1, g2 belongs to g and x belongs to x, right? X is given already. So what does that mean? That means that your g1 cossets of gx with respect to g1 are same as this, right? Clear? Uh, so what does that mean? That means so this implies that so g2 inverse g1 is element of gx, right? Is clear? Because when two courses AH equal to BH, if and only B inverse A belongs to H, right? So that's them. So but they are element of Gx. What does that mean? That means they fixes X point to us, right? So that means G2 inverse G1 dot X equal to X, isn't it? And hence this is nothing but G2 inverse dot G1 dot X equal to X, right? This the second property of group action, right? Now we multiply both sides by G2, and then what we will have? So we'll have, and using the first property of the group actions, we'll have G1 dot X equal to G2 dot X. Okay. So what does that mean? That means you see whenever phi A equal to phi B, then A equal to B. So that implies, thus this implies phi is injective. Is clear? Phi is injective. So what does that mean? That means the map I define from the orbit to the left cosets of the stabilizer of the same element is actually injective map. Clear? This much is clear to everyone? Okay. So if this is injective map, then I know that these are subjective because I assume that both are finite set. Okay. Okay. So yeah. So I need to. I don't know that both have same kernelity or not. So let me define fine. Let me prove this by also surjective map. So how to prove the surjective map? So let's see. So I need to find out that given any left cosets there will be a pre-image, right? So let GGX is a left coset of GX, then the image of G dot X is GGX, right? This is simple because phi of G dot X is nothing but GGX. So this is kind of trivial to check the phi's onto phi's onto, and hence phi is a bijection, right? So I don't know the phi is homomorphism or not because I don't have a group structure always. Because this stabilizer may not be a normal subgroup, right? But I at least know that this phi is a bijective map, and thus what does that mean? That means this cardinality of this orbit, number of element orbit, is nothing but number of distinct left cosets, right? And this is nothing but the index, right? So index of Gx on this. So this is proof. So thus the number of elements in each orbit is same as the index of um, index of the stabilizer, index of the, okay, so let me write down the stabilizer here, that is much better. Stabilizer. Okay. So this is clear to everyone. I hope you can understood that. Okay. Yes. So, but one question one may ask. Okay. So, yeah. So one may ask one question that is it for a given x this is same, right? But how do you know for given two different x and x1 and x2? Now the question is that whether if x1 and x2 are inside the set G, inside if they are in the same orbit, then they are stabilizer has same element or not, and that question answer you can write down by this, right? So now this is just observation, and note that if x is related to y, that means they are in the same orbit. Okay, then cardinality of gx equal to what? So you just from here you just take that cardinality of the orbit of x is nothing but order of the group divided by the order of the, this is the formula for index, right? Order of the stabilizer, right? And hence order of the stabilizer is nothing but order of the group G divided by the order of the orbit, right? So I have the same property as order of the group G divided by order of the orbit, right? But because x and y are related, so they have the same orbit, right? So gx and gy are same, the orbit are same, right? So we can talk about the cardinality of, right? And thus this implies this is nothing but same as clear. So this is a nice observation. Whenever you have two elements they are related, that means they are in the same orbit, then what happened? Then this nice thing happened. Then their stabilizer has same number of elements. The cardinality is same, right? Okay. Yeah, and now I am going to define another notation, and then we will have this one of the most important formulas called orbit stabilizer formula. Before that, let me define one more thing. So um, now for each subgroup, whatever subgroup we choose, so we define something called fixed set of H, fixed H. Okay. So what is that? So this is the element of, so okay, so let me define it. This is the collection of all the element of X inside X, such that this fixes by every element of H. For all H belongs to H. Clear? This is okay. So and obviously you can define for single element also. So also for any single element, so we define something called fixed set of the singleton G, and this is nothing but what? This is all the element of X belongs to X, which are fixes by G dot X equal to X. Okay, and for set I am defining by this notation H dot X equal to X for all H belongs to X, right? So these are few nice notation. Okay, so now with the help of all those things, let us now define the most important theorems of today's class, and that is called the orbit stabilizer formula. Okay, so what does it say? It says that suppose we have a finite, suppose G is acting on X and and you have a group which is finite, and your x is finite. Then you can write down the cardinality of x in terms of this nice pattern, right? So how you can write down? Then you can write down your x, the number element of x is in terms of something called number of fixed points of capital G full set plus some nice things. What is the nice thing? This is that this index of Gi. I'm writing Gi where this Gi is Xi stands for this distinct process, okay, and this um, Gxi's are not the full subgroup of G, so they are proper subgroup of G, right? Yeah. Obviously, before proving this thing, I will prove that there are some equivalent statements. So I will give you a proof, but a few statements are equivalent that I need to tell you, and then you will understand. Okay. So what happened when your uh, this Gx? Okay, so as a subgroup, they are proper subgroup of G. That's what I'm saying. What happens if they are full subgroup? That I will tell you. Okay, and that will gives us the trivial fixed points that I will tell you. Okay. Okay. So let us give a proof. So maybe I can just give some of the um observations. So you see observations or remark. Before going to the proof, let me give some remark. So if for some x, if gx equal to g, then what happened? The full, then what happened? Like stabilizer is the full group. Then what happened? Then what is the meaning of stabilizer? Then this gx is collection of all the g belongs to g, such that g dot x equal to x, right? Uh, in this case, what happened? This is g, right? So what does that mean? That means g dot x uh, is equal to g for all g belongs to g, right? Clear? And this means what? This means x belongs to fixed set of g. Clear? By definition, you say, remember definition of fixed set. Fixed set of age is all the x such that h dot x equal to x for every h belongs to h, right? So if your stabilizer of any element become the full group, then that element actually belongs to the this nice set fixed point of G. Okay, fixed set of G. Clear? So what does that mean? And conversely, 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 what happened? Conversely, uh, if x belongs to fixed point of G, then what happened? Then G dot x will be equal to G for all will be Gx for all G belongs to G, and this implies that um, Gx is nothing but G, right? Because Gx is collection of all the G such that which fixes X, and this is true for every G belongs to G, so Gx is equal to X. So what does that mean? That means the following are equivalent. Yeah, so for the special actions I will add some more thing, but right now the following are equivalent. What are the following? That Gx equal to G, and number 2, x belongs to this fixed set of G. Whatever notation you write down, it doesn't matter. Okay, so these two are equivalent, right? Now with the help of these two, now let me give you the proof of this orbit stabilizer formula. Okay, so the proof of orbit stabilizer formula. Okay, so remember that G is acting on X. Okay, and this action gives you an equivalent relation, and then that makes equivalent classes, right? So you can write down X is union of this joint union of equivalent classes G x's, right? So this x's are element of X, but I choose this joint union means either these orbits are same or equal, so I choose only those distinct orbits. Okay, now if you have to count the number of elements of X, then number of elements of X will be equal to sum over this number of element, right, of Gx. And here the sum is so let me write down the star sum. Star sum means uh, this joint these are this joint union, right? Now we already showed that out of these elements of xi, few elements will be in point of the fixed point of G, right? And few will be not, right? So let us just divide those two sets. So one set will contain all the fixed points of G. So let me write down that is fixed set of G. So those cardinality, and plus the remaining one. The remaining one, what? Remaining one will be those whether these x's are not belongs to this fixed point of G, right? They are not an element of this, right? So I divide the full set into two subsets. One which contains all the elements which are fixed and the fixed point of G, and the set which are not inside fixed point of G, right? Now for these fixed point of G, why I am doing this? Because for these thing we just proved that this is equivalent. So what does that mean? That means if X does not belong to fixed point of G, then your stabilizer is a proper subgroup. The stabilizer cannot be equal to the full group, right? So in this case, what happened? This xi if not belongs to this fixed set of G, and then what happened? If only gxi are not equal to G, right? Clear? So with the help of that, I can write down this, that cardinality of x equal to fixed set of G plus all those xi such that gxi's are not equal to G, and then order of the orbits or cardinality of the orbit. But we already proved that the number of elements in the orbit is nothing but the index of gxi, right? So I can write in the that by this notation plus some index of g xi's inside G and gxi's not equal to G. Clear? And this you can further also, either you can write down by this or you can write down further one more step, that fix of G is plus summation gxi is not equal to G order of the group G by order of the stabilizer, such that these stabilizers are proper subgroup. Okay, so this is the final result, and this result is called the orbit stabilizer formula. Okay, uh, so let me stop here. This is a new idea. I think I should not discuss too much things in a single lecture. And please write down your comments if you have any questions below the comment sections. Okay, I will try to answer all your questions as soon as possible.